Hello everyone, welcome to my talk. Today I'm presenting our work which aims at finding undefined behavior bugs in the kernels. And this is joint work with Yahui from Facebook and our advisor Long. So first of all, what is an undefined behavior bug? Basically, any computation that yields an unpredictable result is an undefined behavior. And this computation are specified by language standard like C99. Mysterious as it may sound, you must be very familiar with these concrete examples like the integer overflows and shift out of bound bugs that I show here. These computations can be dangerous once the undefined behavior is triggered, like the multiplication overflow can actually lead to kernel memory corruption. And these errors are generally identifiable and instrumentable by the UB sanitizers, which is what our work has been focusing on. After talking about what is undefined behavior, let's see what are the damages that undefined behavior can cause. First, we had the survey of undefined behaviors related vulnerabilities listed in the National Vulnerability Database. It turns out with simple errors like integer overflow, a wide range of problems can happen. I'm talking about not only denial of services, but also kernel memory corruption, privilege escalation, and arbitrary code execution, depending on how the undefined behavior affects the system. Another interesting consequence, which is not included in this survey, but also very interesting, is that undefined behavior can make a code unstable. This is a study by Xi Wang, and this study shows that compilers, especially at the high optimization level, can take advantage of undefined behaviors to make the binary code smaller. And sometimes the code removed by compiling this manner can be very critical. Besides all the bad things that can happen because of undefined behavior, according to our survey, 72% of these vulnerabilities are directly triggerable through input from user space. And this is kind of scary because, the triggerability of a vulnerability being decided by the user space is always a bad thing for the security of the operating system. Like the piece of code I show here, the user space input taking control of how many bytes to allocate is always a bad idea. So another nasty thing about undefined behavior, besides it can cause various consequences, that it is hard to get rid of entirely. Take the shift out of bound error we show here as example. This shift can go out of bound because this variable underscored comes from user space. What we usually do is that to place a check for these two operands right after this instruction. And in this case, this is indeed a bug, so a warning will be raised. However, if you look at what is followed in the original code, you can see that this value is sanitized in its own way. So many times when you see a UB warning, most likely you have to look at the code following it to make sure that this is not sanitized. And this poses a big false positive problem for static analysis as well as dynamic analysis. So generally, a precise detection requires going beyond the UB trigger instruction. Lastly, one normally will assume that for a UB trigger instruction, the undefined behavior will normally be sanitized around this instruction. But unfortunately, this is not the case. Previous study shows that, and if you just analyze precisely the enclosing function, the false positive are just too many for others to bear. So overall, a precise and scalable inter-procedural analysis is desired for detecting undefined behaviors. So let's take a look at how the previous work detect undefined behavior bugs. And here's a brief comparison between the typical static methods and dynamic approaches in UB detection. A static analysis usually uses a precise intra-procedural symbolic execution aided by a scalable yet inaccurate inter-procedural static analysis. So in terms of scalability and code coverage, they are pretty good. But as mentioned before, the bug reports produced in this way are generally too many to validate. Thus, this is not precise and it requires a lot of manual efforts. A dynamic approach like the kernel fuzzing usually can be applied to the whole kernel, but it's stuck with its own shallow testing problem. In terms of precision, unlike the static analysis, which usually produce bug reports that are not actually triggerable, dynamic analysis has an advantage of ensuring the triggerability of this bug. However, like we mentioned before in the previous slides, it didn't look at the code after the UB triggering instruction. So it still produced a lot of bugs that has already been handled. So in our work, we designed a precise and scalable static analysis aided by an on-demand data tracking and function summary. Thus, we're not only scalable, but also precise. So let's see how our framework works. First, we also start with a potential triggerable UB instrumentation. For example, we have a pair of values whose addition may overflow. And for this particular variables, we do a backward control and data dependency slicing out all the relevant instructions and variables that actually affect the triggerability of this instrumented bug. And to answer this question, whether if this variable is controllable by user space input, if there is at least one variable that affects the bug, but it's not from user space, for example, like I show here, the triggerability of this addition overflow depends on these two parameters, function parameters. And then in this case, record these two variables and look up whether these variables can be tainted in the function summary generated by the taint analysis. As in the example, the three functions which can call this potential buggy function, and the parameters marked in red are those tainted ones, tainted parameters. And in this case, we choose only the func3 as the caller since it taints all the dependent parameters. After the caller are decided, we do a backward slicing again until we determine that this undefined behavior is controllable by the user space input. After we know that this undefined behavior can be reached by user space input, then we build a symbolic constraint based on the path we've collected during the back tracing process and invoke the SMT solver to tell us if this bug is triggerable or not. If not, then this definitely is not a bug. And if so, we still cannot get a firm decision due to the post-bug checking we mentioned before. So we further advance beyond the UB triggering instruction and make sure that this UB indeed affects the system in a meaningful way. Then we'll report this bug. To illustrate our core idea, allow me to use an example of how we search for undefined behavior in our design. And this is a bug we found and later patched by Linux kernel maintainer. First, we'll start from the potential UB site. As you can see here, the minus operation marked in red can be analyzed locally to be potentially buggy. However, if you look at a enumeration definition, this legal range is actually from 0 to 8. So if you consider this probably, you will probably think this is not a bug. But at the same time, you must know that although the size variable is an enumeration variable, an integer, which is 32 bits, can be passed in. So in this regard, a warning might be raised. However, if you look at this caller, you'll find that this enumeration variable is a member of a struct. And this struct is also passed in as a pointer. Although there is a sanity check here, but it doesn't matter for this particular bug. So we will not include this if condition in our constraints. Then in our analysis, we'll go further to where the truth reveals itself. It turns out that this struct is entirely fetched from user space, which means that the 32-bit integer, which pretends to be a harmless enumeration variable, can indeed be any variable of an integer, and this undoubtedly will trigger the integer overflows at the UB instrumentation. As a result, the return value of this function is controllable by the UB, causing security implications. In the meantime, during the backtracing, you can see that there is a lot of optimization to alleviate the path explosion, as we are aggressively pruning the callers and variables that do not introduce user space input, saving us a lot of time to scale up. So in evaluation, we evaluate our work to find that how many new bugs it can find, and how are the false positive and false negatives, and why, and how much time is required to run the whole framework. For the new bug that we found, we apply this work, KUBO to the latest Linux kernel and find 23 new bugs. given that the Linux kernel has been extensively tested against this kind of bug, among which 14 are confirmed or patched. Another 2 cannot be fixed due to various reasons, like the bug happened in the driver for the legacy hardware. So this influence of the bug cannot be analyzed. For the rest of the 7 bugs, we believe them to be true, but we didn't get any feedback, so we'll see. In terms of false positives, we manually validate the bugs produced by KUBO. In the latest Linux kernel experiment, I found that our false positive rate is much lower than the previous works that use inaccurate static analysis. The source of the false positive mainly comes from that we did an incomplete job of post-bug checking. In post-bug analysis, we only did inter-procedural check, and it turns out that some bugs are vetted in another function after the UB is triggered. But fortunately, these cases are not too many. And in terms of false negatives, it is a little higher than the previous work, which virtually has no false negatives. And the source of false negatives mainly comes from our focus on the user space input rather than other kinds of input, like the input from hardware or the input from internet. As also, we did a simple loop unrolling strategy, which also did some damage to the false negative there. Lastly, for the overhead, as unsurprisingly, most of the time is consumed in the backtracing and symbolic checking stage. And overall, the whole framework uses 32 hours to finish, which we think is a reasonable time. Finally, we realized that this work has its own limitations, which we think might be interesting for future exploration. The first is to refine the post-bug analysis to further crack down the false positives. And the second one is to incorporate the hardware input analysis work to support the hardware or internet incoming input. Lastly, although we didn't experience the past explosion problem too badly, and we didn't have the false negatives coming from this, but we did have a manually set numbers of paths of limited paths, and which potentially can do some harm to the completeness. Well, finally, thank you all for listening. Thank you for your time. I'd like to take a few questions here.